Well, welcome to Thursday night pre-calculus. I am so excited to be once again joined by Vicky Carter, Steve Kokoska, Tom Dick, and my name is Curtis Brown. We're going to be talking about roots of polynomials tonight. We'll be really looking at all kinds of different things this evening. I've had a quick look over the problem set that Steve has provided, and these guys put a lot of work into it back and forth, all three of them, giving feedback on these problem sets. And so it's really a nice set of questions to help your students get ready for the pre-calculus content. If you haven't already, you can download that in the description down below. So click on that little option that says more, and then you can click on that link that's there. Also, you'll note that Steve has a banner for his pre-calculus book up on his screen there, and I'll put a little bit of information about that down in the chat tonight.
Thanks, Bruce.
And so really excited to get this evening off and going. So, Steve, I think I will turn it over to you.
Thank you very much, Curtis. Great to be with you and Vicky and Tom again. Curtis, I meant to ask you, did anyone from the Facebook group send you an email about completing your homework for this evening? I tried to get some people to write to you. I'll get someone one of these days.
Oh no, I definitely got one.
Oh, you did? Okay,
Maybe
good. I'm glad.
two.
Okay, good. Good.
I
Okay.
won't call them out though.
Okay.
I want to.
All right. Well, tonight we're going to take a look at all things polynomials. And as usual, Curtis, I'm going to show a little bit of technology with the TI-Nspire. I'll try to get through at least a problem at a time, and Vicky and Tom will help me along the way, and then I'll hand it over to Tom, and he'll do some technology with the TI-84. So we're going to start out in problem number one with the polynomial function p defined as 3x squared minus 3x minus 5. It's a quadratic. And the first thing we want to do is find the zeros of that polynomial p. Well, it's a quadratic. And the very first thing I tried to do, and I don't have a lot of my scratch work here, Curtis, but the very first thing I tried to do is to factor that. And I couldn't see a nice way to factor that. And I'll probably mention this again this evening, Curtis, but although not part of the AP pre-calculus curriculum, or it's not tested, is this process of knowing what are the possible real factors, zeros of that polynomial by taking a look at the coefficient on x squared and the coefficient on the constant, and taking a look at their factors. Now we're not gonna do anything with that, but some teachers do in fact talk about that with their students, which I think is wonderful. So all right, I got stuck, Curtis. I couldn't factor that, so I had to use some technology, and here's what I did with the TI-Nspire. I started over here on the left-hand side on my left screen by defining this function p. And as we've talked about before, there is this handy function in the TI-Nspire called zeros, and it will find the zeros of any expression of this polynomial in particular. And what I've done is something extra here. I've actually stored this in a list that I call Z. And I like to do that. Whoops, sorry about that. I like to do that because I might want to refer to those values, those z's, and I can do that if I use this function zeros. So notice too that it gave me back those zeros in exact analytic or symbolic form, which is really cool. But if you think about the AP exam, often what they ask for is a numerical value. And so I just did a quick trick here and took that list Z and multiplied by 1. You might be able to see that little decimal after it. That's a quick way. That's a way that I use here to convert numbers, values in a list into decimals. So there are two of them, I think minus 0.884 and 1.884. On the right-hand side, just to confirm this, and another way to do this is on the graph screen. And so I've graphed that polynomial p over here on the right-hand side, and I did a little bit with the x-min and x-max, y-min and y-max, so that I could fit some important points in here, so that I could see the important features of this graph. And then built into the Nspire, as there is in the 84, there's a function that will allow me to find the zeros. So I did that actually twice. And when I did that, I kept those values on the screen. And TI-Nspire, the TI-Nspire has a built-in way to change how these expressions look called attributes. And so I changed it so I could see 3 digits to the right of the decimal, which is sort of the standard for AP pre-calc.
So
So I
Steve,
feel pretty good about this. I'm sorry, go ahead.
no, I was just also going to mention that students are expected to know the quadratic formula. So I think it would be really good in the classroom to do the paper pencil part and then see if
Absolutely.
they are getting that same the zeros that you have with the radicals in it. That's what it should look like.
Yeah, and in fact, too, one thing that often strikes teachers, students too, is that if you take a look at this expression, it's sort of backwards of the way that
Yeah, it
we
is.
write it. And you see that there's a minus sign also factored out of that one on the left-hand side. So it's not always in the exact form that we would get it with a piece of paper and a pencil. But excellent point, Vicky. Yeah. Okay, B, determine whether the vertex of this corresponds to a maximum or a minimum. And we want to give a reason for our answer. Well, there's nothing too deep here. This is a quadratic polynomial. We know that it's the graph of a parabola. And we know that this one opens up by simply taking a look at that constant, that coefficient on x squared. It's a positive 3. And therefore, we know that this parabola opens up. And therefore, we know that the vertex corresponds to a minimum. Nothing else there. I can see that and I can confirm it by looking at my graph up there on the right-hand side. Good. I'm still working, forgive me, Curtis, here. I'm still working on being good at this remarkable device, trying to scroll up and down. It's still a little tricky for me, and I don't know why, but there we go. In part C, I want to find the average rate of change of this function p on the interval -4 to 1. Well, okay. And I apologize for this. I actually used f in there. I should use a p here. This is p of 1 minus p of -4 over 1 minus a -4. That's just the formula for the average rate of change over that interval -4 to 1. So I took 1 and plugged it into the polynomial and got a -5. I took -4 and plugged it in. I got a 55, did a little subtraction and simplification, and I got a -12. That's the average rate of change of that function p on that interval -4 to 1. In part D, we want to find an equation for the secant line for that function p on that interval -4 to 1. Well, that average rate of change that we just found up there in part C is the slope of the secant line. Now, there are 2 points that I could use here that are at hand. I could use 1 minus 5, and I wrote off to the side here. I could also use -455 if I wanted to. I know that those are the 2 points, or are 2 points on the graph of P that the secant line passes through. So an equation of the secant line, and I'm actually going to go over here to the right-hand side first. This is the way that I learned it. An equation of the secant line is y minus y1 is equal to m, the slope of the secant line, times x minus x1. But another way that we often see this in AP pre-calculus is we bring this minus y1 to the right-hand side and just immediately write the equation of the secant line like that. So let me see if I've got this correct. So y is equal to y1, p of 1, plus this m, which is -12, times x minus x1, 1. And I did a little bit of simplifying. I know that p of 1 is -5. And let's see if I did everything correctly. I ended up there with a -12x plus 7. For those of you who have been reading the scoring guidelines, and I apologize, Vicky, Tom, I didn't check tonight. Are the scoring guidelines up there yet?
I haven't seen them yet. They're not up for calculus either, so
No, I wonder why.
I don't know.
Anyway, when you see the scoring guidelines, often they will show these 2 methods for finding the secant line, showing finding the secant line with either one of these points. So I've included that here also. I could use this point -455. So y is equal to p of -4 plus m, which is -12, times x minus x1 in this case, which is a -4. And fortunately, I get the exact same value or exact same expression, -12x plus 7. Good. Thanks for putting up with that. In part E, we want to sketch a graph of the function p and the secant line on the same coordinate axes. Okay, well, this is pretty easy to do on the TI-Nspire. I adjusted my x min and x max, y min and y max a little so that I could see the secant line and the graph of p. If you can see the colors, Curtis, I'm not sure if you can, but the blue curve is p of x, and the green curve is a graph of the secant line. I did not mark this on the graph, but here are the 2 points that it goes through. This was what, 1 -5, and this one over here, I think, was -455.
Yes.
Pretty good. Now, F says, let's use that secant line to estimate the value of p at x equal -1. Let's stop there for just a second. That's an awful lot of words here for just asking me to take x equal -1 and plug it into the expression for the secant line. That's all we have to do. And I've done that down here. So I've evaluated that, let me call it that function y, that line y at -1, and I got a 19. I'm going to sneak back up to my graph. Here's -1 right there. And if I evaluate the secant line at -1, there's the value I get, which I think, what is it, 19. So that's the point,
Yeah.
-1, 19. Now, the question is this an underestimate or an overestimate of the actual value, p of -1? Well, we can look at that graph that I have up there in E and see that it's an overestimate. That 19 is certainly above, what was it, -1?
You've got it on the next.
Do I have it down a
Yeah,
little bit
it's
lower?
below, it's off the
There
bottom
it is,
there.
-1,
Yeah.
1, thank you.
There
There
you
we
go.
go. -1, it's certainly above. So we know that it's an overestimate, but how do we reason that out? And it's an overestimate because the graph of P is concave up. It's a parabola that opens up, so it's always concave up. And that means any of these secant lines must be above that curve. And so my estimate here has to be above an overestimate of the real value, p of -1. And you can see that, I think, visually in this graph, which has the graph of p, the graph of the secant line, and the 2 points, the point on the graph of p and the point on the line. Pretty good.
So
Tom?
Steve, yeah,
Yep,
let me
I'm
just real
sorry.
quick while Tom's getting ready to show us some stuff.
Yes.
So this was a fairly simple polynomial being a quadratic, but what
Yes.
students need to be able to do is carry this process through with other polynomial functions and understand that that concavity is going to tell them a lot about where the secant line is and about whether it's an over or underestimate.
So Vicky, if a student had a more complicated polynomial, and let's just say it's a 4th degree polynomial,
Okay.
and they were asked to find the equation of the secant line, and we can do that. We can follow through this process and we can draw it. And now if the question is it an overestimate or an underestimate, how is the student on the exam?
I
How are
mean,
they supposed to determine about concavity?
I think the fact that it's a technology active question and they can visualize the graph, they may have to hold their finger across the screen of the calculator to say, oh, that's where the tangent line is, but they should be able to use the graphing piece of the calculator to help them visualize what's going on.
So for right now, we would say, look, draw the secant line, sketch the secant line together with the graph of the polynomial, zoom in if you have to,
Yeah.
and when you answer the question, make sure you talk about concavity.
Yes. Yes.
Okay. Tom, all yours.
Okay. All right. Let's see if I can do this. Okay. All right, I'm going to try to share my TI-84. I'm actually using the online version of the 84. That's been working pretty well for me, and so I like using it. And just a quick comment. Steve's shown some things with the TI-Nspire. at least screenshots of those. Vicky and I are also big fans of the Nspire. I think we all recognize that lots and lots of folks using the TI-84, and that's why I, want to give it some airplay time. And TI-84 is a really powerful machine in lots of ways. It doesn't do the computer algebra, but there's so much you can do with it. So I'm going to launch right into this and get to my y equals menu and go ahead and enter that quadratic that Steve was analyzing. So we've got our 3 times x squared, and arrow down, and let's see, minus 3x plus 5, I think, or minus 5. Is that right?
Yeah, minus 5.
Excuse me. Okay, let's get that entered. And then let's do just a quick graph. I'm going to take a misstep on purpose here. I'm just going to go to my usual window I usually like to go to, is Zoom Decimal. But it's maybe not the best window for this particular polynomial. For example, the vertex of that parabola is off the screen. So something we could do to fix this a little bit is go back to Zoom and go down to, well, let's keep arrowing down. There's more. Oh, Zoom Fit. Now, what Zoom Fit does is it actually samples the function across your X range and figures out what a good Y range would be. As simple as that. So we'll try Zoom Fit. And you can see that looks pretty good. If you're wondering what's this kind of crazy stuff along the Y-axis, well, I think that's just a whole lot of hash marks. Okay. In fact, if we go back to our window and actually check it out, notice your Y min and your Y max. The Y max is really huge here. So what I'm going to do is go ahead and change the Y scale. I think I'll change it to 10. Could even use 20. Graph that again. Okay, now those little hash or tick marks on the Y-axis, now those are each worth 10 units. So we get a pretty good feel for this. That looks pretty nice. Great. Okay. Something I did want to illustrate with the 84, and this is something it's interesting. I found a lot of people aren't necessarily aware of this, but I'm going to go ahead and do calculate. That's the shift second of trace. And notice 0 is one of the options there. So let me go down to 0. And let's see, let's get that 1 on the left first. It's pretty near 1. So let me go a little bit to the left of 1.
-1.
Excuse me, negative, right. Yes, it's a little bit to the left of -1. That's right. Put a left bound there. Let's go a little bit to the right of -1. And we're pretty close to the 0 there. Let me just hit enter again, and we'll there it is. And that looks like a familiar number. I think that's a number that Steve came up with. And here's the thing not everybody's aware of. You notice that that's the X value that's been calculated as one of the zeros. We'll calculate the other 0 in just a minute. But I just want to show you that if we quit from the graph screen, that value is in X currently. So if I actually go to the calculator screen and bring X up, there it is. In fact, we see it to more accuracy than what was displayed on the graph screen. So who knows, we might want to store that away, or we could leave it here, but it's now safely on the calculator screen. And so if you're going to use that value for something else, you've got access to it.
Which is similar to Steve doing the saving it as a list. You're kind of making a list on the calculator screen.
Yeah. So I could, for example, store this in maybe alpha. Let's use R for root. Okay. There it is. So now R is safely stored away. If I go back to my graph and do the calculate again, we'll do a 0 again. This time we'll go to the one that's to the right. It looks like it's fairly close to +2. It looks like I'm to the left of it. So let me go ahead and hit enter for a left bound. Go to the right of it, get a right bound, maybe get closer to it in the middle, hit enter for my guess. And there it's homed in on that 1.8844373. And again, if I quit the calculator screen and just bring up X again, that value is right there. So we could store that. And
Oops.
Where are you going to store it, Tom?
you had a problem where
we
you
go.
want to use them, you could. Go ahead, Curtis. I'm sorry.
Oh, I was just giving you a hard time because you froze up.
Oh, I see. Okay. My internet.
Tom,
You
Tom,
stopped with where you were going to store it, and I just was anxiously awaiting. Where are you going to store it?
Tom, I have a question, and I apologize. Sure. You may have answered this one before. I know that you like to use the stat list editor.
Uh-huh.
So if you went to the stat list editor now.
Okay. So I went to stat, and I'll just hit edit. Now
if you just went way over to L1 in the first cell, yeah. Can you type R there, and will it place it there?
Let's see. I'll put in alpha R. There it is.
Well, that's pretty cool.
In fact, if I go up there and actually put my cursor right on it, notice at the bottom, I got a lot more accuracy displayed down there at the bottom than I do in that small cell. That small cell, it's kind of been forced around it for display to 3 decimal places. But it internally, it's still keeping that as accurate as it possibly can.
Okay.
Looks like.
And that is important on the AP exam. If we needed to use one of these 2 values for another calculation, you want the stored value that the calculator is holding on to, not that rounded value.
And just for fun, I'm basically building a list of zeros like you had, Steve. I'll put X in the second cell. And again, if I hover over that, I see it in a lot more accuracy. So this would be like your
little known fact. The number of digits displayed there is greater than the number of the digits displayed on the calculator screen. So if you really want to know the full number of digits that you've got stored, always stick it in a list editor and then go look at it.
Oh,
in other words, if you want to write longer.
If you want to write a lot more digits, that's the place to get them.
Yeah, so it has 13 decimal places. I mean, 13 digits to the right of the decimal points.
Right.
So can you do the same sort of thing, Curtis and Tom, Vicky, on the on a table where it has ask and you can plug in an independent value?
You could dump that into ask. Yeah, absolutely.
Okay.
I bet Tom even could demonstrate that.
So here's.
Oh, look at that! His table's already in ask form. Seems like
yeah, kind of left over.
We may have done this recently.
So this is a good check, Tom. Throw in R right there, and what should be the value of Y1?
Well, we would hope it's pretty close to 0, right?
Should be pretty darn close to 0.
Okay, all right.
That's pretty darn close.
Okay.
Well, you know what we can do? Let me go ahead and put S in too. No surprise there, but let me go actually hover over those zeros. Oh, it's getting it.
It's really, yeah.
It's I just wonder whether there might be a 0.000, 12 zeros and a 1 or something like that.
Well, I think this is very cool, Curtis, because, just looking ahead, we frequently want to build a table of values for a variety of reasons. And often we have to go to the graph screen and find a value there numerically, which is not an integer, which is not a rational number. And it's very nice to be able to store this exact value or this value to so many digits and use it in a table like this. I think that's very cool.
Yeah, very nice. If it's okay, there was another thing I'd like to show us.
Sure.
Let's see. Let me quit. Go back to the calculator screen. And that interval for which you were doing average value and
Yes.
plotting a secant line, what I wanted to do is go ahead and take those two endpoints of that interval. I think it was -4.
Yep.
And I'm going to store that in A. Okay. And I think the second value is just 1.
Yes.
Store that in B. So this is my interval from A to B, happens to be -4 to 1. And then I'm going to go to my y equals menu. And in Y2, what I want to do is kind of build your secant line equation from those two values. I've got them stored in A and B. So what I'll do is, let's see, I think what I'll want is evaluate my function, y1, at A.
I really like this, Tom. This is nice.
Yeah, it's very cool.
And then we'll add on. Now I'm going to actually do the slope here, the slope formula. So let me do this little fraction thing here. Let's see, it's going to be y1 of B minus y1 of A.
Mm-hmm.
That's my numerator, difference in the y values, over B minus A, the difference in the x value. Now let me get out of the fraction. We're going to multiply that. That's actually the slope expression. We're going to multiply that times x minus A. Now, just a quick reality check here. If the x value is equal to A, then everything I've got there in that second term disappears, right? Because I'm multiplying by A minus A is 0. So I'll be just left with y1 of A, which is at the front end of that. Let me see. There we go. We see the y1 of A there. If I put in x equal B, well, then I'll have a B minus A in the denominator of my slope expression, and I'll have a B minus A factor over here. Those will cancel, and I'm going to end up with y1 of A plus y1 of B minus y1 of A. Well, that'll be y1 of B. So it's kind of guaranteed to go through those 2 points at the right places. So let's just graph this and see what happens. Boom, there we go. There's our secant line, just like that. And I think that looks pretty similar.
Yeah, it's cool.
Steve had.
So Tom, do
yes.
one more thing. Go back to the y equals.
Okay.
Okay. You can copy that y2 expression, right?
Okay. You mean put it in like y3?
Y3. Like
okay.
y3, and change the A's to B's.
Ah, okay. I got it. Okay. So let's see, for the copy.
Hey, Tom, go to Y3 and press second in the store key. That gives you the recall.
Yeah.
And
then you can recall Y2.
Got it. Okay. Thank you for the assist there. I needed it.
I'm sitting here thinking copy paste as the Inspire does, and I'm going, okay.
I honestly
you can recall Y2 and that'll paste it.
Great. Okay.
All right. Now just
change.
And
now we'll just edit it. Yeah, we could have used
chalk that one up for Curtis not doing his homework, but knowing the calculator.
Yeah. Curtis to the rescue.
So I'm just going to interchange all my A's and B's. I'll make that
actually, you only need to do the first one and the last one.
That's
Your slope's
true,
fine.
because the other will, if I interchange both A and B, it'd be the same thing.
Yeah, it's negative over negative, whatever.
And let's see.
One more space over.
There we go. Make that an alpha B.
Yeah. So we should get a different color that overwrites the red line that we had, right?
All right, let's give it a shot. See what happens.
Yay.
There it is. Yeah. So there's 2 different ways we could have done that. Very nice. Yeah. Very nice. People might be wondering, well, why didn't I just do that all with -4 and 1 directly in the y equals screen? Well, the reason I did was if I wanted to play around and look at some different secant lines, I would not have to re-enter anything other than store new values for A and
Yeah.
B.
Mhm.
So that makes it very, very easy. So, for example, if I went to the calculator screen and stored like, say, -2 for A and +2 for B.
Oops, that's a 5, but that might work
Oh,
too.
whoa,
Yeah, that might work too.
why
Yeah.
not? Let's do it anyway. I mistyped, but we're just playing around here. Here we go. So I entered those two. If I go back to my y equals, well, I'm not going to edit anything at all. I still,
Yeah.
want my same parabola there, but the y2 and y3 will have different.
Yeah, they're good to go.
Oh, there's a new secant line, and this one is
Wow.
going through points corresponding to x equal -2 and x equal 5. So very
And
cool.
Tom, I'm going to give
Yes.
another reason for the power of what you've just demonstrated is that arithmetic to have found, for instance, what was it, -455 or something like that, that
Yes.
55. I mean, how often have we seen students make a careless mistake with the arithmetic? And this could maybe, if they used a technique like this, give them a clue that something's wrong with what they have calculated or evaluated as they tried to write that tangent line. I mean, that secant line, I'm sorry. So, I mean, there's a lot of power to what you've demonstrated here.
Yeah.
Agree with that.
Moreover, I just wanted to point out one more kind of really powerful thing about that is if when I go back to my y equals, if I changed y1 to a new function, I've still got the secant line ready to go. Right? Okay. So this is a very, very general secant line equation for any function that's stored in y1. And again, and for any values A and B that you'd like to store away. Pretty neat. Okay.
Oh, we need to do that, Tom.
What's that?
Oh,
a new function? Okay.
Change something in y, change a constant somewhere in y1 and then just graph again.
Okay.
We might not get it all on the screen, but I don't know.
How about a 2 instead of a 3?
For the leading coefficient?
Yeah.
Okay, let's try it. New parabola, but
New
the
secant
line
lines.
that's
Hey.
going through the two values.
I
That's
just
right.
saw a fabulous question pop up in the chat.
Okay.
And that does not mean to disparage any previous questions, but this one I love. Could you potentially replace A and B with lists of variables, and then be able to get more than one secant at once? I believe the answer would be yes. So you could store your A's as list 1 somewhere and store your B's as list 2 somewhere, and then drop those in there, and I think you would get a family of secant function or secant lines.
Very interesting.
Yeah.
I don't know whether I should go ahead and try that.
I mean, doing that live on
Yeah.
TV might be.
So wait a minute.
challenge.
So wait a minute. This is a great idea. So what if you keep B always the same,
And keep
like
making,
So
3,
just make
and
A and
let A vary and get closer and closer to B? Could you do that in a list?
Oh my gosh! Oh my gosh!
Well,
This is.
I do have yet another idea if you'd like.
Oh, shoot. Go ahead.
Well, there is an app.
Oh, good. Let's see that.
If you go to apps, and this is one of those apps we were just talking before we went live. This is one that I discovered kind of late in life. Didn't realize, just how powerful it was. But it's you scroll all the way down there, you see transform there. And so I'm going to enter that. I get this kind of information screen. And if I go to y equals, whoops, let me try that again. There we go. I'm going to go ahead and change that y1 to our original function. I think we had a 3
Okay.
there.
Yep.
And you can see that y1 and y2 are highlighted, but they have this kind of interesting thing to the left. These two, the first two y's in your y equal menus, y1 and y2, are activated for transform. And what that means is any parameters like coefficients or powers, whatever, they have the labels A, B, C, or D, are active for kind of stepping through different values. So for example, if I were to graph this, notice that my A is currently -2, my B is 5. If I hit the right arrow key, notice that the equals on A is highlighted. A is
Yes.
active. If I hit the right arrow key, it will increment A to -1, and the secant line changes. I increment to 0, now I get a different secant line. I could change B by arrowing down to B. Now I'm going back, I'm using the left arrow key to make those different values. So you could explore tons and tons of different secant lines. Now, this is not quite the same as having a list. I think people were envisioning having all the secant lines drawn on the same graph. That's a different thing, and that could still be worth doing. But I really love this transform app. It basically kind of gives you the a kind of a slider, if you will, like you have on Nspire, but on the 84.
Is there a limit on A and
I
B?
just tried the secant line thing, by the way, with the list, and it works great.
Cool.
Okay. Maybe
So
we should have you
to answer the
your
question, Gerald, yes, you could. You could do that.
Tom, is there a limit on A and B?
Limit in what sense?
Down at the bottom here, could I type in, for example, could I type in A equal -4.5?
Nope. No limit.
-4.5? Is that what you said?
Yes.
Or yeah.
Boom. There it is.
Okay.
Hey, I'm wondering if I could put in R.
Ooh.
I'm not sure.
Okay.
I'm working without a net here. I'm not sure. You know what? That's what I want with the graphing calculator.
I'm your
I
spotter,
often say,
Tom.
I don't know. Let's
You're
try
good.
it and see what happens. You know?
Okay.
I'm your spotter, Tom. You're good.
Holy
Wow.
Toledo.
Oh,
Good
I
work.
like it. There's that
So
0.
it brought that in from outside the app. It's still.
Oh, absolutely. Absolutely.
Yeah.
Yeah.
And it was stored away. Now, this was why it was good we had it stored in R, because, you know, we had done some stuff with X. We found another 0 and things like that. And I could go down to B and put in S. Now, I think I know what that secant line is going to look like.
And I hope any
It might be
students that are
pretty
on here
flat.
can think about this too.
Ooh.
How about
Wow.
that?
Through the 2 zeros, so it's laying right on the x-axis there.
How about that?
So very fun stuff. And
Cool. So Tom,
Yes,
there
go
was
ahead.
no C or D here, but just for the heck of it, if you went back to the Y equal menu
Mhm.
and where it has -5, if you put in plus C, would now that extra parameter show up?
Yep.
Now, I don't know what the
Yes.
value of it is right now, so
Yeah, it's probably, well, it's whatever's been stored in C. It could be, the default is 0.
Default is 0, but I think for the transform app, if you do that and you use it, I think it puts a 1.
okay.
All right, let's do the graph.
Ah,
Oh, that makes sense because
Yeah.
0 could give you some pretty
0 gives you a lot of really boring
degenerate
graphs.
graphs, really. And I don't mean degenerate in a behavioral sense. I just mean not interesting. Okay.
Well, lazy.
Lazy graph.
Lazy graphs. I like it.
Yeah. Though 0 would not be bad as a value in this setting. It
Yeah.
would be perfectly good.
So
Huh.
real
As
quick.
a coefficient, that's a problem sometimes.
So
Yeah.
real quick, Tom, make C2.
Make C2. All right. Okay. So I'm going to arrow over to C, put in 2. Or I could have just gone over there and incremented it.
hit the arrow.
But there we go.
Yeah.
And
Maybe a little incremented a little more. Make it like 12. I forgot the
okay.
tick marks were 10.
Okay.
I really like what the visualization that we have here and the discussions that teachers could have with students about what's going on and having them think. I mean, we're actually now transforming the graph, but they're no longer zeros, but they have a very important place on the graph as far as those two values that we have in for A and B right now. I think it's a great visualization.
Yeah, this is really cool. I mean, that tells
Yeah.
us something about their relationship to the vertex. I mean, that's really
Mhm.
neat. Yeah.
Right, right. Yeah. And the two Y values are matching, but they're no longer zeros because we're
Right.
looking at the whole graph up. Yeah.
Yeah.
It's just an incredible, the transformation app, it's just a really incredible environment for doing some graphical explorations. So I highly recommend people to check it out if you're using the 84. Look at things to do. And we'll revisit it again a little later. So think I should turn it back over to Steve here.
Okay. Thanks, Tom. That was cool. That was fun. Okay, Curtis, here we go with number 2. This one's a little shorter. So we have a graph of a polynomial function shown in this figure. And I just want to remind you, I have some reminders for myself off to the right-hand side there. This polynomial function here has a restricted domain. The points marked with a solid dot are on the graph. And so over here at the point labeled A, that point is on the graph of P. Over here at this point labeled G, there's an open circle that is not on the graph of P. So maybe another way to think about this is if the domain, the restricted domain of this polynomial is from this value on the x-axis to this one, this is included in the domain. I might put a square bracket there. This value is not included in the domain. Okay, so with that said, with a little bit of background about the annotations, what they mean in that graph, we want to identify each labeled point as corresponding to a local min, local max, Holy Toledo, global min, global max, or a point of inflection, or possibly none of these. So let's see if we can quickly move through these and identify them all. The point A. This is a good one to start with. This is actually a local maximum. And the reason in AP pre-calculus is because it's an included endpoint of a polynomial that has a restricted domain. Now, for those of you who also teach calculus, AP calculus, that might not be true a little bit depending upon the book you use, but in most cases, we would not consider that a local maximum. But in AP pre-calc, we do. The point B, that's a local minimum. Why? Well, because the polynomial switches from decreasing to increasing. That is one way to think about it, and I think an AP pre-calculus way to think about it. Here's another way to look at this. It's a local minimum because if I take a look at what I would call a neighborhood of that point B, if I look at just a little interval around B, that's the smallest value in that neighborhood. That Y value corresponding to the point B is the smallest value of that polynomial in that little interval in that neighborhood. Similarly, the point C, that's a local maximum. Why? Because the polynomial switches from increasing to decreasing. I'm at the top of a hill or the top of a mountain. Another way to look at it, at the point C, the Y value is the largest value in a neighborhood of C. The point D. This is kind of hard to see, but that's actually a point of inflection. Why? Because the polynomial switches, the graph of the polynomial switches from concave down to concave up. I'm sorry about this, Curtis. My graph's going to get a little messy. But here, the graph of P is concave down, and right there is the point of inflection where it changes now to concave up. D is a point of inflection. Let's see, E. Well, E is actually got two names here. It's certainly a local minimum. Why? Well, because the graph of the polynomial switches from decreasing to increasing. And again, the y value corresponding to e is the smallest value, the smallest y value in a neighborhood of e. But e is also a global minimum. Why? Because the y value corresponding to e is the smallest value of that polynomial over its restricted domain. Cool. F has two names. It's a local maximum. The polynomial switches from increasing to decreasing. It's also the global maximum. The y value at F is the largest y value of that polynomial over its domain, restricted domain. Although you can't see it on my screen, it is there. What's going on at the point G? Well, we've got to have one of these. It's nothing. It's not a local minimum because it's not included in the restricted domain. So it's not a local minimum. There might be a tendency to think that. It's not a global minimum. It's not a point of inflection. The graph doesn't change from from concave up to concave down there. It's nothing. Cool. Vicky, could you help me here? Could you add anything on this?
Hey,
Go
Steve,
ahead, Curtis. Yes.
at point D, would it be acceptable in AP pre-calculus to say that the slope of the curve changes from decreasing to increasing?
It would probably be more appropriate to talk about that the average rates of change are changing.
From the average rates of change are changing from decreasing to
Yeah.
increasing. Yeah.
Yes,
I think
because
that makes sense.
pre-calculus, we don't necessarily talk about instantaneous rate of change.
Yeah, we don't.
We
Yeah, we
talk
don't.
more
We
about
kind of
average rate of change. Yes.
we kind of think about it a little bit, but we're still in pre-calculus.
Pretty
Yeah.
careful. Yeah.
Yeah. So
So
what the only thing I would say is that students may notice that there is a point of inflection not designated that would be between E and F, but we
correct.
don't have a name for it. And what we really want students to do is sort of just get a sense of as they move their hand across the graph, where do they kind of feel like it's changing from concave up to concave down when they're moving from E to F, and that's approximately where the point of inflection would be.
Vicky, I think a student would be more likely to see a question like this on the multiple choice portion of the exam.
Yes, yes.
And so in that case, they wouldn't necessarily have to provide a reason, but on the other hand, it could be one of these questions where it says something like, well, the point D is a point of inflection because, and you would have to know why.
And you'd have 4 choices of
Right.
explanations, and you'd have to pick the correct one out. Yes.
Yes. Yes. So you wouldn't necessarily have to write one, but boy, you've still got to know why it's true. Yeah.
Yeah.
You've still got to know why it's true. Cool. All right. Shall I try 3 here, Tom? I don't think there's any
Sure.
technology in there, but let's give 3 a shot. So in 3, we have another polynomial function p. This is a 4th degree polynomial. We're going to do several things here. We're going to first try to find all the zeros, both real and complex, of this polynomial. Okay. Well, how the heck am I going to do this one? So one of the very first things I thought about once again was, what are the possible real zeros here? What are the possible real roots? And okay, so in my class, I would teach this idea of, well, I'm going to look at the factors of 30, I'm going to look at the factors of 2, and I know what some of the possibilities are, and I might try some synthetic division. But another, maybe perhaps quicker way to do this is to start out with a graph. Let's work visually. And so I graphed this polynomial p, and Tom reminds me all the time to say something about this. The behavior of the polynomial, the graph of the polynomial p, does not go crazy beyond -3 and +3. In other words, the behavior is the same off the graph or continues in a similar manner. So as I look at that graph, I see 2 real roots with multiplicity 1, I believe.
And how would we know that it's multiplicity 1? Students should be
Well,
able to explain that.
exactly. And the truth is, it could have odd multiplicity.
True,
But
true.
it could have odd multiplicity. But knowing what's ahead here, knowing what's coming, okay, yes, they've got multiplicity 1.
So we would have a curve that's tangent to the x-axis, either above the x-axis or below the x-axis if we had multiplicities that were even, like a double root.
Correct. A double root, or even if it were multiplicity 4, that's correct.
Yeah.
Yep, that is correct. So what I did over on the right-hand side was I used this command once again that you've seen already on the TI-Nspire. I used this command zeros, and I found that these two zeros were at -2 and 3/2. And I'm looking over at my graph screen, and yeah, I think that does correspond. Over here is -2, and yeah, that's between 1 and 2, so there's 3/2. Okay. So here's what I did, and there are probably other ways to attack this, but I've still got to work on finding the other roots, which are complex. And so what I did is, if -2 is a root, I know that x plus 2 is a factor. If 3/2 is a root, I know that x minus 3/2 is also a factor, but I'm going to multiply that by 1 in a convenient form, 1/2 times 2. And I'm going to use that 2x minus 3. I know that that's a factor of this polynomial. So what I did in this next step is I multiplied those two quantities, those two factors together to get this quadratic. I know that that quadratic divides evenly into this original polynomial. So down towards the bottom here, yeah, I know it's painful, but I use long division.
Well, the students have to know how to do long division, so this is a good practice for them.
Painful, but I did it. And fortunately, the remainder down here in the bottom right-hand corner is 0. It should be. I know that 2x squared plus x minus 6 is a factor. My other factor is now a quadratic, which it should be x squared minus 2x plus 5. So, okay, let me skip to the next page. I already know what the roots of this quadratic are. Now I've got to find the roots of that quadratic. So up at the top of this page, finally, I'm going to get to use this quadratic formula, which students are expected to know. See, the coefficients there are 1, -2, and 5. So minus b minus 2 plus or minus the square root of b squared minus 4ac. I did a little bit of simplifying. And I've got the complex roots here are 1 plus or minus 2i. Curtis, we haven't asked many questions of you lately or the participants. What do we know about these complex roots of a polynomial? Do
They
we know
look like
anything
conjugates.
special about them that you can tell me?
Did you hear me? They look like conjugates. Am I on mute?
They do indeed. And what is true about complex roots of a polynomial? They always come in conjugate pairs.
Yeah.
Okay?
Mm-hmm.
They always come in conjugate pairs. So I
You
haven't.
thought you had me, didn't you?
No, not at all. Not at all. I know you're on the ball here. So the zeros of this polynomial are -2 3/2, 1 plus or minus 2i. And I just wanted to show you this very cool feature on the TI-Nspire. It has a built-in function called C-zeros. So it will actually find all of the real roots and the complex, real zeros and complex zeros. And I did the same thing here. I stored them all in a list in case I wanted to refer to one later on. And there they are, 1 plus 2i, 1 minus 2i, -2 and 3/2. And son of a gun, that's kind of nice and easy to read too. That's kind of cool, the way that I might write that.
So I like that this is a problem that actually kind of starts with using technology, and then we see how the technology gives us a means of doing some algebraic work to, find these. This is really kind of beyond what you'll probably see on the AP exam, but I think it's good practice for the students to kind of have that combination of algebraic work and technology work.
Good for tomorrow morning at 8 o'clock. Tom, do you have any technology on this one, sir?
Actually, I do. It's not
Okay.
kind of specifically for this one, but there was something I wanted to show if I could.
Okay.
Give this a shot here. So I'm going to hopefully share my TI-84 online.
Got it.
And what I've done is, you remember that transform app we were talking about on the 84? I've still got that running. By the way, if you're running that transform app, you see up there at the top where it says plot 1, plot 2, plot 3. You do want to actually quit the app when you're done using it, because I think it kind of keeps your calculator running and can run your batteries down if you don't formally quit it, even if you're not using it. So anyways, my y1 might look a little bit funny, but what I've done is put a polynomial in there of in factored form. And so I'm using up A, B, C, and D, all 4 of them. And those are my 4 zeros, or my 4 roots for my polynomial, using the thing that Steve was just mentioning. That is, if A is a root polynomial, x minus A would be a factor. So in factored form, let's take a look at what the graph of this looks like. Now, I have some specific values in for A, B, C, and D, but you're going to see them in just a minute. There we go. Okay, so I've got a graph. In this transform app, you can see at the bottom, there's a placeholder for all 4 of those zeros, A, B, C, and D. And I've got -2, 1, 2, and 3. That should be where this graph crosses the x-axis. And if we take a look at it, looks pretty good. So that's nice, but what's kind of cool about the transform app is we could change the values. For example, I'm going to increment A by 1, so it actually has the same value as B. What that means is that -1 is now a double root, or it has multiplicity 2, and you can see the effect that has on the graph. That double root, my graph actually kind of comes down and just kisses the x-axis. It just bottoms right out there. If we did that with C and D, whoops, let me put A back to where it was. Let me arrow over to C. Let me go ahead and increment it by 1. So now I have a pair of double roots there. One thing I haven't thought about, but was kind of, I started thinking about as Steve was doing his discussion of this number 3 on his problem sheet, was somehow doing something. I think you could only do 2 complex numbers, because I would need 2 of these parameters for each complex number. It's a couple of complex roots or something like that for a quadratic. So something to explore at another time. But again, I think this is kind of a cool use of the transform app, is using your 4 parameters, or however many you want to use, as not just coefficients, but actually as root values. That's it. I'll turn it back over to you, Steve.
Beautiful.
Right.
I think we can finish this one up very quickly, Curtis. The last one.
Well, you
And Tom, this polynomial,
you don't have a lot of time.
Yeah, this polynomial P at the very top of this, this would be an interesting one to put into Y1.
Yeah.
And use the 5, 3, 4, 7 as your A, B, C, D.
Oh,
this would be kind of cool to do. So anyway, here's a polynomial. It is in factored form, and we're asked to find all the real zeros of P. So since it's in factored form, the zeros are really easy to pick right off of that expression. They are -7, -4, 3, and 5. We're asked to describe the characteristics of the graph of P near each zero, and we've been talking about that now in the last couple of problems here, referring to the multiplicity and the behavior of the graph near each one of these zeros. Well, x equal -7 here, the multiplicity of that root is 1, so the graph of P must cross at that point. And by the way, another question here is to ask about, well, is it positive to the left or positive to the right as it crosses? And how would you figure that out? We'll leave that as sort of an open question for now. X equal -4, that has multiplicity 3, odd multiplicity. So once again, it crosses at that point, -4, 0. At 3, that has multiplicity 2. It's an even multiplicity, so the graph is tangent to the x-axis. And finally, at 5, it has multiplicity 1. So again, it crosses the x-axis at the point 5, 0. We haven't talked much about limit notation at all here, but here's a quick one down here in C. Use limit notation to describe the end behavior of this polynomial. Well, I took a look at that factored form and realized that the leading coefficient when I multiply everything all the way out is 0.0025x to the 7th. And that's what I really need to look at to determine end behavior. As x increases or decreases without bound, what really determines the end behavior is that component of x with the highest power. So that's x to the 7th, and the coefficient on that is positive. So let's see, as x goes to minus infinity, as it decreases without bound, x to the 7th, that's going to be larger and larger negative, also multiplying by that positive 0.0025, still large negative. And this is the way that we write that in mathematical notation. The limit as x goes to minus infinity of p of x is minus infinity. Similarly, as x goes to plus infinity, p of x is increasing without bound, going to plus infinity. And finally, here's a sketch of that graph. And I had to do a little bit with, again, with x-min and x-max, y-min and y-max, so that you could see all of these zeros, so that you could see the behavior of the graph. Again, notice over here at that root, I think it was a 3. It just comes up, the graph just comes up, and its tangent just touches the x-axis and turns around.
So, Steve, real
Pretty
quickly,
cool. Yes, go ahead, Vic. Sorry.
in many of these questions, it would be about a polynomial, maybe not quite as complex a polynomial that you have, but it is highly likely that the students will be asked to describe the end behavior of the polynomial, and they'll only give one, either as of the polynomial p as x decreases without bound,
Yes.
or as x increases without bound. And I think students need to read very carefully and make sure they answer the question. They have allowed for the last 2 years that if they wrote them both down and they were both correct, but there is no guarantee that that's going to continue. So students need to make sure they're focused on whether it's decreasing without bound or increasing without bound, and write the appropriate limit.
And I would just add before we quit, Vicky, I think I've seen some multiple choice questions where
Yes,
they're given a polynomial and the question is something like describe the end behavior, and there are the 4 options here,
right.
right? And
Yeah, you
so,
got negative,
right?
negative, negative, positive. Yeah, all those
Yeah.
combinations.
Okay, thank you, Curtis, Tom, Vicky.
Thank
We'll
you.
Thank
post
you
all of
guys
this
very
tomorrow.
much. That was fantastic information tonight. Fantastic. I always a good time. Always learn a little bit. Also, always enjoy the possibility of an exploration on the 84 CE. Um, and the good stuff we can
Yeah.
always learn there. So, really quickly, I just want to let everybody know if there's a teacher still around, they can always email me for a uh, certificate for hour of professional development. I think you guys can reach out to me there. I put my email in the chat, so you should have an opportunity to reach out to me there, Curtis at TI.com. We will go ahead and get the solutions posted here pretty quick. So
Get 'em to you
we'll get
tomorrow,
those
Chris.
up there for you guys to be able to use with your students. And yeah, have a great evening. We'll be back on here in about a month.
Very good.
Right.
Good night. All right, let's see. I'm gonna watch the deal. I think we're probably